All right, so this is the last section that we're going to be doing in chapter 13.3. So this deals with what they call arc length parametrization. That's a tongue-tied one this morning. All right. So anyway, basically this finds an inverse of a function. So instead of, like, for example, giving you a time and say, what's my location? I want to know, here's my location, what time, or where I am. So basically I'm just switching my scenarios around a little bit. So I'm manipulating my function to give a different outcome. Anyway, let me explain this by going back to Calc 1. Okay, so, and then it'll make more sense here in a second. All right, so let's start off with this basic question you had way back when. Say, find the area under the curve f of x equals x on 0 to 4. Okay, so let's draw a visual here. And I said use something real basic here. So we have, here's my equation, y equals x. And basically given x equals 4, x equals 0, what is the area of this function? Now we could just do by simple geometry, but we need to use the integration here for this thing here. So basically this implies by integration that if I integrate from 0 to 4 x dx, I get x squared over 2 from 0 to 4, and basically my area would be 8. Alright, so now if I want to change it up and just say instead of x equals 4, I just want it in terms of x equals some numerical value, a general equation. Okay, so I'm looking for a general equation. That would mean then, if I come back to this piece here, the area that I would be finding would be x squared over 2 from 0. Now we do have to have a starting part from 0 to, let's use t, because that's what we're going to be getting into. Okay, so instead of x equals that, it would be like t equals a. Alright, so that would mean then a would be t squared over 2. And what I can do now is actually solve for my time. So this would be 2a equals t squared. Therefore, t will be the square root of 2a. Okay, which means then what I can do then, now this is the same thing as x here, is come back up and substitute in for up here. So what I have then is now an equation f of a. So I have an equation for the area, which would be the square root of 2a. So basically what I found here is what we refer to as a type of an inverse. So now instead of giving you, let's say, x equals 4, I'm going to say what happens if I have now the area, oops, why is that doing that? I have no idea. A equals 8, so f of 8. Therefore, if I plug this in, I have the square root of 2 times 8, which is 4, which is my x value. So therefore, my x value is 4. And then I could quickly find my y, f of 4 would be 2. Excuse me, f of 4 would be 4. So basically I'm doing the inverse. So I'm switching equations around. So instead of going from direction x to the area, I'm reversing the process. And this is what sometimes your equations, especially like chemistry or physics, and you're saying, well, I want area. So let's say, what happens if I have an area and then I want an x value? So you can reverse the equation in terms of what you want to find. So let's say, for example, I have an area of 16. What would be my x value? Well, that would be the square root of 2 times 16, or the square root of 32. So I can quickly find other values if I want to reverse my equation, or basically refer to it as the inverse of this. So let's do another one just like we did in Calc 1 with this concept before we go to a parametric equation. All right, so let's say we have a function f of x equals x squared, and we're going to find the area between 0 and 3. So let's draw a visual here. So we got parabola, x equals 0, x equals 3. We got the area here. Okay, so now we got to do it by integration now. So the area is going to be represented by the integration of 0 to 3 x squared dx, which would be x cubed over 3 from 0 to 3, and the area will be turned out to be 9. Okay, now let's find the general equation. Okay, so from right here, let's switch it around. So we're going to do area equals x cubed over 3. And like I say, we'll be dealing with time here. So technically I probably should just go ahead and use x. But let's go ahead and use t here, just so you can see a little bit different variables. So area would be t cubed over 3, which means t cubed would be 3 area. Therefore, t would be the cube root of 3a. Now keep in mind that actually should be x. Okay, which means now I can change my equation in terms of area instead of x and y. So I would have now f of a, and that would be the cube root of 3a squared. Okay. Now, if I threw in my area here, let's say f of 9. Now this would be, I keep this 3a to the 2/3 here. So let's say my area is 9. That would be 27 to 2/3, which would be 9. So likewise, so then if I want to find, so if it's my x value, my f of 9 in terms of here, okay, that would mean then that would be 81. So basically reversing concept. Okay, all right. So let's do one parameterization, and we'll kind of take a break here. Let you think about it for a little bit. So what this is called is arc length parametrization. Okay, so basically it's referred to as an inverse. So we're switching things around. So basically, we're finding the inverse by a distance. So what we're doing here is we're switching the time or distance, and by what I mean by distance or location, around. So given, instead of time, find my distance, basically distance, location, find the other direction. Switching things around here. All right. Now, something to remember is how to find distance. Okay, so on a parametric equation, so given a parametric equation, RT, remember that is found, and we'll use S of t, which is the integral of a to b of the magnitude prime dt. Remember, that's a magnitude. Okay, so you got to do the derivative squared, use Pythagorean theorem, and integrate it. Okay, so let's use an example. All right, so, and we're going to do something simple here. We're going to do RT, a linear line here. So we have 1, 1, 0, and T of 1, 2, 3. Okay, so let's find my link. So you got to first find R prime of T. So that would be 0. Derivative T is 1. So basically I would have 1, 2, 3. So the length here, S of T, or sometimes you might see this as S prime of T. So we're going to integrate it, 0 to 4. And by the way, I didn't give the time here, 0 to 4. 0 to 4. Now once we do the derivatives, now square, so 1 squared plus 2 squared plus 3 squared dt. So we would have the square root of 14, 0 to 4 dt. So, and I drew that, so square root of 14 from 0 to 4 dt. And that would give me 4 root 14. And that would be my distance. Okay. All right, so now let's find a general equation. All right, so the general for the distance S. Now let's take this piece here and replace this. Now we are starting at 0, so we have root 14 from 0 to t dt. Oh, excuse me, all right, that should be dt. We already did that. Oops. Actually, there was a dt there, excuse me. I kind of got in a hurry there. I did poor notation there. Let's say S equals root 14, 0 to t, and there should be a t here. And therefore, that would be t root 14. Sorry about that. It's a little bit I did a little bit better on my notes. So therefore, t is S over root 14. So what I can do now, if I come back to what my RT was, so my RT was 1, 1, 0 plus T, comma 1, 2, 3. So basically, I'm going to replace the T with this piece here. So therefore, you have R of S now, and I have 1, 1, 0, and now S over root 14 of 1, 2, 3. Okay, so I've basically switched my equation around because I want to work the other direction. Okay, so let's check it here. Now, prior up here, we had a distance of 4 root 14, I do believe. Okay, so we had a distance of 4 root 14. So let's check it to see if it works in terms of it gives me my location at t equals 4. So now, I probably should have done this. So let's just see. So I think when we evaluated up here at 4, if I put 4 in here, I should get a point of 5, 9, 12. Okay, so now if I put my distance in, I should get the same thing here. So now plugging in here, I have 4 root 14 of 1, 1, 0, plus, now my distance is 4 root 14 over root 14 of 1, 2, 3. So that goes cancel out. So I have 1, 1, 0 plus 4, 8, 12. And adding those up, I have 5, 9, 12. So now notice I got my location, which is the same as this. But notice I've given in terms of a distance, I can find my location, or I can use my time to find my location. Okay. So anyway, that's kind of what we're doing. We're going to take a little break, so I'll let you kind of think about this, and then I'll give you some more examples with something more than just a linearization problem. So we'll do different functions and do the same process with that. Okay.